I think the most important thing I noticed is that at least 3 talks mention that diffusion is not a black box. And I think this is an important message we want to also bring to the HBM community, so think exactly how you set up your analysis. So is there any question from the audience? Can range from the most basic question about, I have this data set, I have no clue how to start to do the analysis, how many directions, what is the best B-value to start the acquisition? Please, if you failed to ask a question, we are here for 10 minutes or more. Yep. You have a mic just behind you.
Hello? Yeah, so I'm usually studying like a disease of white matter or patients, and I always wonder, like, there are many methods like BSS that you can find like a group difference like in just a part of a tract. And I wonder, in terms of physiology, how probable is that some disease or disorder will affect just a part of a fiber tract, if it's really realistic or it's like just an artifact of the methods we're using.
Thank you. Anyone want to think? Alex, maybe you want to say something on that? Yeah.
Well, so first of all, I've got a disclaimer. So I'm only a simple physicist, so I'm not really an expert on the clinical part. But I can appreciate what your concern is, that, you know, if you have got some pathology that you may think that more than just a small, tiny part which, you know, lights up on the TBSS skeleton is affected. You know, my suggestion there is to use a kind of, you know, multi-analysis approach where you're also looking at other ways to analyze your data. So we've mentioned a few ways to analyze your data. It might be useful to actually have a kind of converging evidence towards a specific structure by looking into this. So we mentioned, for instance, tractography, looking at an entire bundle, but there's also something called, you know, a long tract analysis, where you basically maybe combine best of both worlds, you know, from a voxel-wise approach towards an entire bundle, where you can have a more specific investigation on how this pathology is occurring. So that would be my suggestion, to, you know, look at it from a different angle as well and see how it, you know, whether this effect is bigger or not than expected. Okay?
Okay. Zoltan?
I would add that there can be actually reasons for why you see something locally. If it's a local injury, then it's obvious. Also, fiber tracts could be damaged all the way through, but you only detect it where they bunch up together in the same voxel or same region. So, for example, if detecting something in the center of the corpus callosum is likely, even though maybe the whole fiber tract is damaged, but the percent of fibers in the other voxels is too low, so the sensitivity is not good enough. So I think just keep an open mind, like Alex was saying, like look at it from different points of view. It could be reasonable that that's what you should find.
Okay, if I can add something else, actually we have a poster here investigating specifically this effect, how the sensitivity to microstructure changes in different voxels might be different simply because the crossing angle is different. So you might have exactly the same biological effect going on, but because the degree of crossing is different, the crossing angle is different. One voxel you need, for example, 20 subjects to see a p-value of 0.5, then the other one you need 40 or 50. So it's likely that you might see spot changes along the track because the sensitivity is different along the track. Anyone else want to comment? Or okay.
Thank you.
Yeah, another question?
Well, first of all, Flavio, thank you for a wonderful workshop. It's been really helpful. I have a question to the last speaker. I might have misunderstood something, but I'm not sure I'm understanding in tractography. If you do a step size that's smaller than a voxel, how is that going to help you if your tensor or whatever you're fitting is fit to a voxel? So how is that going to give you better results in terms of tracking?
So that's where interpolation comes into play. And so your neighboring tensors or your neighboring local fiber orientations will influence. So if, for instance, let's say you're in the center, you would trust your direction inside the voxel. Let's say you're in the corner, you're much closer to the bottom triangle, let's say, of other voxels. And so these voxels will pull you. So if you watch back my talk, the drawing where I was following the jagged line versus the interpolated line, that's a bit of the effect you see with interpolation.
And what your recommendation for step size would be relative to the voxel?
The MR-Trix paper and our group have been pushing for about 1/10 of the imaging resolution. So let's say on a 2 millimeter grid, that would be 0.2 millimeter. But I've seen accurate results, also good results at maybe half the grid or a little bit, but definitely not the voxel. If you're jumping from one voxel to the other, you'll jump into different white matter bundles.
Okay.
So 1/10 of the grid would be my recommendation.
Okay, and one more question. I see that you're suggesting that instead of the FA threshold that we've been using, we just use white matter masks, and that's going to constrain our tractography. What would you suggest in the cases where white matter segmentation isn't that good, as the case is with stroke patients?
Yeah. That's a good point. It's a good question. We often go back to FA when that happens. Or we take, actually, if you look at one of the last slides of Flavio's talk about the fiber ODFs, you can actually use the amplitude of the peak, the maxima, as a threshold. So that the smaller peaks are like random noise, so you would avoid these peaks, but as soon as your peak is large enough, you're confident in that peak. So a lot of the Hardy toolbox now use peak amplitude instead of FA. But if you're stuck using FA, I would use FA, but lower your threshold down, and then clean up your results with good anatomical priors, I would advise. So at least allow your tractography to explore the structure with low FA thresholds, but then you'll get a lot of probably not nice looking tracks.
Even more fake positive.
Yeah, but you'll clean them up with good anatomical priors, if you can. Well, maybe the others are tractography experts as well. Maybe they have a recommendation.
Well, maybe a quick comment. So if you've got pathology, then obviously the pathology itself will affect or may affect the diffusion process in such a way that it distorts your orientation profile. I mean, take the extreme case where you have, basically a cavity filled with fluids. Well, there's no tissue there, so there's no anisotropy, right? So doing tractography there, you can do it, but you don't want to do it because it doesn't make sense. So that's also something to keep in mind, that if you've got some pathology which really, affects the orientation information, then it may be actually, advisable not to do tractography at all in that region. Okay.
Okay, next question.
Yes, hi.
Hi.
It seems from the symposium that fiber crossing seems to be a problem, but not only for tractography, but also for quantifying, like FA, for example, or MD. So I'm wondering what would be your recommendation if you want to quantify white matter, with what method to use today with a validated method.
Okay. Well, there is not a problem to use FA or mean diffusivity per se, because the FA mean diffusivity per se, they're answering one question. They're answering what is the mean of the tensor and what is the anisotropy described by the tensor. So as a general metric, say what's going on inside the voxel, FA and diffusivity are giving anyway any information can be useful. The problem is this information, it might be difficult to interpret. For example, if you have a crossing sometime and one fiber degenerate, your FA might actually increase because the crossing effect is the dominant component, and when you lose one track, you remain only with a single track, so you have an increase on FA. So you can still interpret. If you know your anatomy, if you know what's going on in your pathology, you might still comment on that. We think that using crossing fiber method, like for example, HMOA, upper fiber density, you can actually see specifically which track is affected. So these are new matrix. For example, I think MRTrix has this matrix, R-Tool, StarTrack has this matrix, I think the DIPA as well, and all these metrics have been implemented more and more in different software. So it would be interesting to see what information, how useful they are. I think they are useful. I think, for example, we applied to some study on dyslexia, and for example, if you do a TBSS or VBM analysis, you see that, for example, corpus callosum, corticospinal tract, and arcuate fasciculus, when they are close to each other, they are all showing some correlation with language performance. But that's because they are sharing the region. When you start to do a track-specific measurement using HMOA, you actually see the only track affected by language is, guess what? The arcuate fasciculus and not the corticospinal tract. So we actually can increase in the specificity and sensitivity of that, anatomical specificity of the measure. But also as well, we have all the microstructure work that can actually add further, because if we can actually distinguish for edema and different tissue, it would be an improvement. But probably better to leave to Gary to comment on this as well.
But then you would have to go through tractography first, and then look at quantifying and in the region that you're interested in.
Okay, so you can do, in theory, we are working on some tricks or some analysis that actually can do voxel-based analysis using spherical deconvolution. There are already other approaches doing that. So in theory, you can normalize and use the FOD to do voxel-wise analysis. Even using BET post-X and TBSS can be done, for example. I don't know how good or bad is the result. I never use this tool specifically. But stratigraphy is not necessarily to do a quantification inside for something voxel-wise. But I think for what we are doing in our lab, we are doing stratigraphy because it's also much better to follow the individual anatomy of each subject. So the arcuate fasciculus is not always the same across all subjects. Sometimes it's bigger, sometimes it's shorter, sometimes it's more bendy. So you need to adapt. If you do a voxel-wise normalization to a template, you might have an effect actually of blurring your statistics because you are not matching apple with apple. You might have actually one track overlap another track when you do just this kind of voxel registration. So that's why we prefer to use stratigraphy. But this, I think, is a slightly different point. Okay, I'll leave the rest to Gary.
Yeah, I think microstructure probably one of the main way, one of the current way trying to address that issues. And I think as Maxime mentioned, actually the future really is trying to combine tractography with microstructure, where you have this, say, the global tracking, which is based on modeling the tracking, derive the tracking together with the signal modeling at the same time, where I think that's where we can actually not only know individually each voxel, what are the different compartments? Could it come from edema, CSF partial volume, crossing fibers? All that information need to be teased out, but that's very difficult to do it in a voxel by voxel basis. That's where combining with tractography really is the key, kind of looking at a neighborhood, looking at the whole brain, and then trying to, really join force and trying to combine microstructure and connectome, and we can not only derive information about each compartment, how they link across different tracks. And I think that's for me the future.
Okay, just to add, I forgot actually to mention that also Explore DTI is measuring these track-specific metrics. I just realized, okay. Okay, I think we have a couple of more questions back. Yeah.
Hi. I have a couple of questions. The first one is about the residual maps that were shown. And the vibrant correction method was suggested that it could be used to correct. Can it be used for any kind of residual maps, heavy residual maps, because of artifact or that fat-saturated artifact? Or
So I didn't get your question properly.
So how do I've seen those residual maps, but I don't know how to correct them.
So the residual map itself is not something you need to correct. The residual map itself merely reflects the quality of the data. Yes. So obviously, if you have got your data, let's say, before and after correction, then ideally, before, or let's say after the correction, the residual map should be, more uniform, or, the residuals should be, smaller.
All right. Is there a tool which I can use to, which uses the residual maps to correct it?
Yeah, I think nowadays most packages provide these residual maps. I think I know at least one that does it, but
I know how to get the residual map.
Okay.
But how do I use the residual map to correct the data?
Well, so again, so you're not using, so it's not a means. So the residual map itself will not help you to correct for the artifact. So you'll need, let's say other tools, tools to correct for subject motion or for Gibbs ringing artifacts. Yeah. These are separate kind of tools, and the residual map is merely a kind of post hoc, quick visualization, or you can quantify it to see what the quality is.
Yes.
Okay?
Yeah, thanks. And one question about tracking. When I do a seed-based tracking, there is a high bias of streamlines at the seed. So if I want to give equal weightage to shorter fiber tracks or streamlines when compared to long range fiber tracks, should I correct for the length, or what do I do to remove the bias at the seed? There are a high number of tracks there.
That's a good question, and I mean, it would take us to a connectomics, I think, workshop to sort of address these. There are a few papers where they try to normalize track count by volume or by length or by surface area, depending on how you do tractography. They show it improves things. To me, it doesn't solve the whole issue. And I think, and maybe the others can help me with this question, but I think it's still a very open problem.
But do you think it'll help if I would like to somehow give more weightage to the long-range fiber tracks if I'm doing a global tracking? Would it make more sense to correct for the fiber length?
At which stage? At the post-processing stage? After tractography?
No, during tractography, there's an option for
sure, okay,
FSL.
I see what you mean.
Yeah,
I would say yes. Because if you're tracking through uncertainty, the further you are, the more unlikely you are to connect, because you have more potential of getting lost, basically.
Right.
So I think in the FSL options, this is definitely something to do.
No. And when you said about uncertainty, does mode of diffusivity give similar kind of information of dispersion or uncertainty? Is there a relation with mode of diffusivity, one of the new metrics?
Okay, I think I can answer that. Yes, I think usually there is a direct relation between anisotropy and uncertainty, because think about a tensor. The more sharp is your tensor, the rest will be affected by noise. Also, actually, the signal will probably be higher because you have more restriction. When you have a very low anisotropic tensor, kind of almost a sphere, just a little bit of noise can make you change a lot your orientation. So there are actually, this is already a paper done in 2005, 2004, I'm not exactly sure. They actually quantify the uncertainty. I think there is one of the first probabilistic topography method based on this, actually PICO, is usually using this assumption that FA is somehow correlating with uncertainty.
But in probabilistic tracking, there is a metric called dispersion, which shows some kind of a measure of uncertainty.
Dispersion? Okay.
There's some dispersion matrix they talk about.
Can you tell us which methods are you referring? Because dispersion, I'm thinking more about the dispersion from NODI, for example, or dispersion of the FOD.
Probabilistic tracking in FSL.
I think that is uncertainty, okay.
That's uncertainty. So I was just wondering if there is something similar kind of information also in mode of diffusivity, the metric, which is derived from the diffusion tensor.
Okay. If I may chime in, so I think the mode is a measure which is different from FA, which is measures essentially indicating how flat the tensors are.
Yes.
Which it actually relates to, usually in a case when tensors become very flat, is because of the presence of crossing fibers. And so these are genuine dispersion, meaning that they're physical crossing, physical dispersion, that is not a single coherent fiber going through a voxel. So the kind of uncertainty measure you're talking about in FSL is really the fundamental uncertainty due to noise of determining the main direction. So they are kind of different things.
All right.
Yeah.
All right. Thanks.
Okay, I think we have time for one last question, or a couple if you have more.
Thank you for the workshop. So the first question I have is a rather big picture question about your general thoughts and comments on looking at these DTI measures within very small regions like the subcortical structures as well as the cortical region. So what are your thoughts on that? And the second thing I'm trying to do is to relate these DTI changes to gray matter atrophy in very small structures like the hippocampus CA1. So due to the limited spatial resolution of the DTI, I'm wondering what can be done and what are some of the potential pitfalls when I'm trying to do that.
I think that there are a number of challenges that you mentioned. I think the spatial resolution is the key, which is also leads to the SNR. SNR is a big issue, not only because of the smaller voxel requirements, as well as intrinsically the deep cortical gray matter structures, for example, are far away from the multi-channel coils we're using. These are small coils, arranged to the surface of the brain, so they have very little sensitivity deep in the brain. So all these factors really reduces the SNR. So I think that will really bias any of the diffusion measures. So I think that's something which need to be kept in mind.
Okay, so I can add that clearly measuring cortical diffusivity with, I would say, 2.5, 3 millimeter voxel is kind of hard because you have a lot of partial volume. So in order to start to have an effective analysis on cortical measure, you need probably to go 1.5 or below 2 millimeter for sure. And we are starting now to do that with the new acquisition from, for example, HCP and a new scanner available. But probably the full answer, you will probably get the full answer to your question in this afternoon. That's why you have to come back later, because there will be a speaker talking about post-mortem imaging, and there we will actually, you can see how far we can go. We can get 100, 200 micron resolution or 3 or more, and we can actually see different cortical layer or things like that. So that, and that also all the gray matter will be kind of revealed to you. Okay.
Thank you very much.
Okay. If there are no other questions, I think we can now...
Can I ask one more question?
Oh, sorry.
I have a question for Gary. So we have some data, DTI data with only one p-value. Would you recommend we fit the naughty model?
As I mentioned, that's probably inappropriate. I would not recommend it myself, but I know people have done it, so it doesn't mean that I would recommend it, though.
And when we try to fit the amical versus naughty, the original naughty, they give us different results. Which one should I trust?
Like I said, I think amico and neither amico nor the original implementation really support single shell modeling for complex multi-compartment models like naughty or any other multi-compartment model. So you wouldn't, for example, fit a DKI model to your data. So I wouldn't recommend you to do that, regardless what you use, amico or the original toolbox.
But if I do use the naughty protocol, which one?
I think, okay, that's a separate, yeah, so for that, I think the amico give you a very good, quick answer, which I think, we had an abstract at ISRAM this year, shows that it does give a very similar trend, a consistent trend, with original MATLAB implementation, but there is a bias. We're investigating where the source of bias, and in terms of fitting quality, I think we find that amico does slightly worse compared to the naughty toolbox. So if you have computing resources, I would say it's safe to use the original one, but to get a kind of a first pass result, I think amico give you that very quickly. I think it's worth doing still.
All right, thank you.
I think there is another question. Yes?
Yes. Hi. I have a question about thresholding probabilistic tractography output. So I have to compare probabilistic algorithm with another deterministic algorithms. How should I choose the threshold and how to justify the choice?
I don't know, to be honest. Maybe somebody can help me here, but because I haven't played a lot with these probabilistic tracking thresholds, so I wouldn't be confident. But I know you'd be comparing, already comparing deterministic and probabilistic is a bit like comparing orange and apples. So I know now FSL or these probabilistic tools often have the options to produce streamlines from them, like the most likely streamlines. So you could try to visualize these streamlines and discretize them and try to find agreement or disagreement this way, but it would be fundamentally very different because the algorithms are completely different.
Okay. Thank you.
I guess if I can, sorry.
Oh, sorry. Go. No.
So I guess, if you can, one way I can think of trying to do that is actually define some well-defined metric that actually all these tools can produce, such as I think the diffusion tractography challenge that a number of people here involved in, which is, regardless what method you use, but you're asking for some concrete output. And those output can be validated, the ground truth. And if that's the case, I think that could form the basis for any comparison.
Okay. That answered your question?
Yes, thank you.
Okay, thank you very much. And looking around, sorry, there is a lot of okay, I don't see any other questions. So I think we can stop here for now, and we are back at, I think, 1. So time for a quick lunch. And thank you very much. Thanks again for all the speakers again.